Motor nameplates. Some people call them legend plates. And so we're going to get this, how to interpret this. Huh? Should be. If it's not, make sure I'll put it up there. So important specs, horsepower. Over here, we're still using horsepower. The rest of the world is using something called kilowatts. Frame, volts, amps, code, service factor, class of insulation, ambient temperature, and temperature rise. So this is the information that's on. We also have a new one. I don't know if it's slide now. The problem we have is we've got two electronic components. That we call capacitors, and I don't like to use that symbol because and then we have inductors. These guys do no electrical work, so they shouldn't get hot because current flow is in and out of them. The analogy I use for these devices for a capacitor is really easy to see. Where I have two buckets filled with water, I wish I could find that animation. And then I've got an AC pump right here, and then I've got another bucket over here, and we'll put a resistor right there. Well, this is the way a capacitor works, in that the pump changes direction, and it'll pull water from one bucket, run it through the resistor into another one, and then when it changes direction, it'll come back through. Well, there's no flow between the buckets. So capacitors, there's no current flow through a capacitor, which means there's no current flow through the capacitor. The capacitor does no electrical work. But it appears like there's current flow through it. So that means if you put an ammeter out there and you put an ammeter and you measure voltage drop across the capacitor because current flow is not through it, then it would measure voltage, and then you would calculate a power. So capacitors and inductors create a power that we call apparent power. They don't do any work, but they appear to do work. So when we start putting these devices in a circuit, it's real weird because one thing, Kirchhoff voltage law says what? What's Kirchhoff voltage law? You ever had that yet? If you had DC, I know you. I think everybody's in this place has had DC. What's Kirchhoff voltage law? These are the laws of the sum of the voltage drops in the circuit should equal to the applied voltage. Yeah. Well, guess what? When you put capacitors and inductors in a circuit, you'll actually get more voltage drop in the circuit than is applied because they're out of phase. Actually, it's a little tricky, and they see it. So we produce a type of power called apparent power. This is what you pay for. Now, capacitors will cancel out inductors, and inductors will cancel out capacitors at a certain frequency. We call it the resonant frequency. So that means if I come in and I have an inductive circuit, which is what the power grid is. The power grid is an inductive circuit because every coil of wire is an inductor. How many different devices out there do we have? Every transformer, every motor. So inductors create what we call a lagging power factor, which means the current lags the voltage. Well, inductors create a leading power factor. So what happens is when we come up here and if we put the right, inductors create a lagging power factor, create a leading power factor. So if we get the right combination, then what happens if we get the right combinations, they cancel each other out as far as apparent power goes. So this is why every once in a while when you're driving down the road, you'll see a power. It's got these three little boxes out there. three little boxes of round ones, some of them are round. Those are capacitors, and they're out there to help reduce the lagging power factor. And then, of course, your substations have a automatic switches around to add more capacitance in the circuit depending on the demand. So what we have is motors to create a lagging power factor. So it's new on the motor, to increase the efficiency of the motor, they'll give you a code where you can calculate the size of capacitor that you need to use to bring that thing back. So that's not on this PowerPoint, but that's new on your new motors. It's always strive to make motors more efficient. By the way, motors, their power factor is better if you run it at rated horsepower. People go out there and buy a 10 horsepower motor, run a 5 horsepower motor, 5 horsepower load, and they're actually paying more current and they're actually getting worse. These engineers sometimes have the ability that, so that's not up here, but I'll see if it's in this thing. So horsepower, originally used to compare the output of a steam engine with the power of draft horses, and it works out to be 550 foot-pounds per minute. So they got all these horses, they tied one at a time, they'd hook a chain up to them, had the load down in a well, and see how far they could pull that in a minute. And then because what was the power that we were using in those steam engines? We were using horses. And everybody wanted to compare it to what? Horses. So that's where they came up with the horsepower. Unfortunately, 5 horsepower motor means nothing because you don't pay for 5 horsepower, you pay for watts, right? You understand that? Yeah, well, everybody. We're about the only, there's only about 2 companies that's still using what we call imperial standard of measurement. Some people call it the English standard. So we're still over here using inches, feet, yards. Everybody else is using metric. And everybody else in the world uses kilowatts on their motor. I don't know. Yeah. Well, most cars, horsepower. A lot of cars are trying to do torque now instead of horsepower, right? Yeah. So yeah, we're still using feet and inches. So we got how many inches in a foot? 12. How many feet in a yard? 3. Right? How many feet in a mile? Yeah. But in kilometers, everything in the metric system, everything runs in tens, right? So we jump all over the place. So they tried to change us over at one time. Some of y'all don't remember that, but they tried to change us over to the metric system. So the cars that came out would have 2 speeds on it. It would have miles per hour and kilometers per hour. And then they put up these mile markers. They also put kilometer markers over there. And on the signs, they put kilometers in miles. And they figured out what would happen over time, what would happen. They'd phase out the miles and go to kilometers. But we're a stubborn country, right? Varies between geographical reasons. Most countries now use what? It's the international standard units of kilowatts. Roughly 746 kilowatts per horsepower. This works out real well when you're trying to calculate your overloads and all that kind of stuff. So kilowatts equals horsepower times, and what we've done is combined a lot of math, right? So 74.6%. And so we can calculate horsepower kilowatts by learning that one number. Are we okay? Yes or no? So what we did on kilowatts equals horsepower, instead of multiplying it times 7, instead of dividing it by 760, we always do what? Use 0.746, which would be kilowatts, instead of multiplying by 1,000. But you can still do it that way. Frame code. So frame codes. This is so every motor is a little different. So and we have to mount this motor somehow, right? Mount, and then we have to attach it to a gearbox. And of course, originally when they came out with motors, and originally when they came out with electricity, everybody was doing their own thing. So you could go to one house and it would have a certain amount of plug, and then you had to buy the plug from the company that made it because it was patented, right? You understand? Well, over time, what happened is NEMA, which is the National Electrical Manufacturers Association, said enough is enough. Let's establish standards. So thank goodness we got standards. So now these plugs that we have against the wall, these are NEMA 15. NEMA 15, which is 15, right? 5, it's standard 5, NEMA 515, which means it was 15 amp plug. A NEMA 520 would be a 20 amp plug. So they standardized that. So now I can go to Lowe's and I can buy a cord. The 240 still got a little problem, but they're still standards. It's when the electrician wires your house, what plug do they put in there? But it's still a standard plug. So now when you go to Lowe's and buy like a dryer, they don't come with power cords anymore because they don't know which NEMA 240 plug that's in your house. So they decided to do this with frames. So the frame specifies how far the feet are mounted apart, how long the shafts are. It's a double sided shaft. It's got both shafts on both sides. Size of the frame. So what this means is that now you don't have to buy the motor that's in your unit, right? Understand? All you need to do is buy a motor that matches or exceeds the motor that you're trying to replace. Because now all these motors are what? Standard. So I don't know if they've got a frame thing inside your book. I don't know if it's in this volts, phase, amps, and service factor. So volts, this is the voltage that the motor is designed to run around. A dual voltage motor would have what? They'll have 2 voltages on there. And you just can't run it, right? We looked at this the other day. You have to wire the voltage motor. You have to wire the motor for the voltage you're going to run it on. So it's just like our transformer, right? So what do we have to do on our transformer? We'd wire the primary of our transformer depending on the voltage that we're going to put in. Phases. We only got 2 phases over here. What's the phase we got? The phase. Our house runs on single phase. Heavy industry runs on 3 phase. So that's specified on the motor, right? The number of phases. What happens when you lose one of your phases? I hooked it up to the ground because we call that single phasing. Full load current. The current draw of the motor when operated at its rated frequency, its rated voltage and load. This rating also assumes the phase voltages are balanced. 3-phase guys, it's almost impossible to get exactly the right same voltage on all 3 phases. So this assumes that it's balanced. They're usually really close, but there's really no way they could be perfect, right? Okay, this makes sense. So amps, this is not how much the motor pulls when you start it. This is the amount of current it pulls when it's running at its rated frequency, its rated voltage, and its rated load. Service factor, multipliers used to calculate how much the motors can safely be overloaded for short periods of time. So our service factor on a motor is 1, which means you can't do what with a motor. You can't make it pull more, produce more horsepower than what it's designed to pull. Everybody okay? So service factor is usually 1.1, so it's like 125%, but they actually give you the multiplier. So they'd say 1.25. That means you would take your horsepower or your current or anything and multiply by what? 1.2, 1.25. Are we okay? Service factor. So this will be on the nameplate somewhere, and it's going to be labeled what? F. Amps are usually called amps. Volts are usually called volts. Like I said, a dual voltage motor has the ability, it will have 2 voltages on there. And what will change with each one of them would be this guy right here. So if you run it at a lower voltage, it's going to have to pull more amps to produce the same horsepower, right? You understand? If you run it at a higher voltage, the motor will pull less amps. So this is the starting current multipliers. So what we do is, I'm glad this is on here. I don't know if I can make it bigger, guys. This chart is very rarely available on the internet. So what we have is we have a code letter on the motor, and this tells us the amount of our multiplier for our start current. So if you got an A on there, it means what? Your current could be 1.5 to 3.15. These are multipliers higher. If you got a V motor, I mean, if you got a U motor on it, this guy right here will take 29.2 times to 22.93 times the amount of starting current. This is the average, by the way. I'm sorry. This is minimum. This is maximum. And this says it's the mean, but that don't work out right, does it? No, this is a chart. So there's nothing, you can't, this guy can't be memorized. So what they're doing now, on your newer motors, they'll have a code on there. Let's see if ours has a code. And it's called code. So this has a code of M on it. So it means this motor right here could pull between 10 to 11.19 its full load current, just getting it what? Started. So when we use 6 to 8, that's just a what? A rule of thumb, right? What you should do is actually, when you start calculating your fuses, this is where you need to go right here. And look at the code. Find this code on the internet, right? You understand? Or come back to this class. You have access to this forever, I think, right? And this should be in the handout section here. Maximum starting current would be, then you'd probably multiply that by what? 1.25. And then if it's not a standard value, you do what? Round up. So 6 to 8 is just a what? It's just a rule of thumb if you don't have a what, if you can't have access to this chart. And it's usually pretty reliable. Okay. Starting current multiplier per code. So like ours is M. And this information is going to be on the nameplate, and what do they call it? They call it a code. Yeah. This is the ambient temperature. What is ambient, by the way? Oh, it's in there. So ambient means what? Yes, surrounding, yeah. So a Class A motor, a Class B motor would have a temperature rating of 130. A Class F motor would have this, and a Class H would have that. Usually, every motor I've seen for a long time is what? 40 degrees centigrade. The motor, okay? This makes sense? Yes, no? Huh? Temperature rise by resistance measurement. So this is a temperature rise is so this would specify the temperature class. This is a service factor. So our motor has a what? These are standard service factors. So this would be, I'm sorry, this is still 1. This is a 1.15. This is service factor. This has the motors, all motors with a 1.15 or higher service factor. These are for what? Enclosed. So frames, we have frames that are, some of them are not totally enclosed. But any motor that's going to run in a very, very harsh environment needs to have to be what we call totally enclosed, which means they have no vents into them, right? Does that make sense? So the motors that are not totally enclosed, the big motors usually have a fan on the back of them that blows motor, blows wind through the motor, makes it circulate. So these motors right here, totally enclosed, would operate at a lower voltage than the what? I'm not a voltage, guys. At a what? Temperature, yeah. So these are lower temperatures, encapsulated windings with a service factor 1 and all enclosures. So these are encapsulated. What do you mean by encapsulated windings? What do you think? Huh? Sealed, yeah. They'll do that a lot on the motor. A lot of times what they'll do is they'll take the stator and they'll actually get it down in a enamel. Why would they do that? Not only moisture, but the problem we have with motors is I showed y'all magnetic wire before, right? And so what we're trying to do with magnetic wires, we're trying to get an extremely good coupling between wires. So what that means is the wires themselves have extremely thin insulation on them. But they're putting that still. When this guy here is generating a north pole, this guy here is generating a north pole. So what's the tendency of these windings to do? Like magnetic poles want to do what? Repel. So the transformers do what? Yeah, they're moving back and forth. So, and the problem is, if you have a lot of motion, the wires can rub against each other, and then you have two wires touch, right? Understand? And then that creates what we call a shorted line. Now the motor can't produce enough current, can't produce enough horsepower because once you change the turn ratio inside the thing, right? So a lot of times they'll take these motors, these transformers, and they'll dip them down in lacquer. Well, as soon as they do that, you dig down in lacquer, and then all of a sudden you got insulation around this, and they get hard, right? Understand? So that means we can't haul it through. If you do that, the transformers will probably last longer because they short out. They can't. They're going to run hotter. All your transformers, your high power capable transformers, will immerse them in oil, and then they'll do a lot of oil. You'll see a lot of your substations where you can see your three big transformers out there, and each one of them has on the side. A radiator over there, just like your car, and then they'll have a fan blowing on there, like that oil, trying to get the heat away from the transformer. No, because grease you can't move. So either they blow air on them, or if it's big ones, they'll actually put an oil. Originally, the oil was a carcinogen. I forgot what they used. They had to go back out and they did a lot of work because they had a plant out in Calera that made the straps. What was that plant? I can't remember. They made the straps for me. The elastic straps, and they went on a strike, and they brought in all these people to fill the spot. We used to call them scouts. And you know what they did? Shut the plant down. Somebody went out there and climbed into the substation and took a drill and drilled a hole in the bottom of the transformers. Let all the line. Let all run out. What happened to the transformers? They burned up. Yeah, they had a guy killed too. Went out there and one of the guys that was picketing ran out in front of the truck. The truck ran over him and kept going. And they caught up with him out on the interstate. That was a long time ago. I don't even know if the plant's still down there. This is not I don't think this was in Clear. I think it was in Columbiana. Yeah. and they had two clamps. They had two clamps. One of them was one of them made the elastic, and the other one made something else. I don't remember, but that's right there together. I used to ride my motorcycle out there a lot. So y'all get up and go to y'all's workstations. Y'all look at y'all's motors and look and see what's on these. So the motor, what's the amps rating? Okay, great, guys. What's the amps rated on motor? At rated voltage, right? Rated load and rated frequency, right? You understand that? What's the service factor? What's the service factor? Well, no, it's how much you can safely overload the motor. So ours has a service factor of 1. My motor, the black motor, has a service factor of 1.15. If you're not running at 208 volts, if you're running at 208, it's got a service factor of 1. So that's how much we can safely overload the motor, right? Not for extended periods of times, but for brief periods of time, right? Everybody okay? Of course, phase, what's that? Single phase, right? Or what? 3 phase. We only got 2, right? The code, what does the code tell you? To start it, right? Gives you the range of currents that motor says it will take. If you can't find that information, then rule of thumb is what? 6 to 8. But like I said, these days, it's hard not to find this information. Used to, we'd have to have all these books, but now, you can do what? You know, looking at frame types, motor frame types, they're bringing up a big old nice drawing, tell you all the frame types and give you all the dimensions of the motor, how long it is, how high it is, single shaft, double shaft, spacing on the mounts. They give you all that information. So any questions on this? So there's a lab where you have to do the nameplate. And of course, if I give it to you on the test, I'll give you a nameplate. So what I've done is, let's see, make sure it's up on. This is not due, but y'all can start looking at it. So what I have on, hopefully it's up there. I don't see I need to put it. I got the nameplate for the motor. Is this slide up there? Somebody looking for that? I don't think the slide that we just looked at is up there either. I need to put it, yeah. And in the handout section, I need to put by the way, I don't know if y'all have looked at this, but on your review sheet, if it says, you know how to define or know the meaning of the following terms, this is a dictionary that I put together, and there's a whole section in here on motor controls. And they're in alphabetical order, so this would be a really good place to go in and look up some of these definitions if you're studying for a test. I think NEMA's even in here. And they're in alphabetical order. And I keyed every bit of this in, by the way. So I need 2 things to put up there. What do I need to put up there? I need to put the nameplate and the PowerPoint slides for All right, guys, what we're going to do, plan for Wednesday, is everybody been able to get text from me now, right? Okay. So it looks like, and I don't know if I'm going to have time because a bunch of computers down here in the room, they don't have Chrome on them. It looks like Chrome might work. But if I can't get Chrome installed on all these machines down here, then we might do our test over in Ethel building. And we can't do it at the end of the class because there's classes in those rooms. So what that means is we'll have to do our test at the start of class. And that's what we'll do. We'll go over there. I'll send you a text. We'll go over there and do our test at the start of class. And then we'll work in the lab in the afternoon after the test. So I'll let you know if we can get these working down here, and we'll be in the lab at the start of class, and then we'll do the test at the end of class. So if we do it at the start of class, that means you can't leave when it's over, right? Because, like I said, every day in this class counts as 2 classes. So I got 2 things I need to put up there. Okay. Got one more thing we're going to get into. We won't finish this lecture, but we'll go to the lab.